we want to write down the Gaussian elimination algorithm. The true magic is the following theorem. The theorem tells us that every matrix is equivalent to a unique matrix in reduced row echelon form. So we start with an m by n linear system, which we have represented as an m by n plus 1 augmented matrix. So step 1 is reading from left to right, locate the first column with a non-zero entry. We're going to call this the jth column. Step 2, if necessary, interchange row 1 and another row so that the first entry in our column j from step 1 is not 0. So basically we just want to have any entry that's not 0 at the top of our column. Step 3, scale the first row by 1 divided by the first entry, the one at the top of column j. We call this one A1j. This ensures that the leading entry of row 1 is 1. Step 4, for each row, replace Ri, the ith row, by the row Ri minus Aij times R1. The number Aij, remember, is in the ith row of the jth column. It's that entry. So what you're doing in step 4 is you're clearing all of the entries below the leading 1. At the end of step 4, this column should have a 1 on the very top, zeros below it. Step 5, ignore the first row and repeat this process until the matrix is in row echelon form. Step 6, to put the matrix in reduced row echelon form, find the first non-zero row starting from the bottom of the matrix. Clear all the entries above the leading entry. Repeat. To get a good feel for this, you have to work examples. Here's one. So we record the operations and the results to put this matrix into reduced row echelon form. The first step is to look at my matrix, scanning from left to right, and find the first non-zero column. That's easy. The first column is a non-zero column. The next step is to ensure that the top of my column has a non-zero entry, which it does. The next step is to scale the row so that the top entry in my column is a 1. Okay, it's already a 1, there's nothing to do here. The next step is to clear the entries below this 1. I can do that by first subtracting twice row 1 from row 2, then by adding row 1 to row 3. Now that I've cleared all the entries below my first leading entry, I move on to the next row. I scan from left to right to find the first non-zero column. In this case, my first non-zero column is exactly where I started from. My leading entry is also non-zero, but it's not 1. So I scale my second row by -1/3 to make it a 1. Next, I clear the entries below my leading entry. The only one is this 2. So I'll subtract twice the second row from the third row. Now our matrix is in row echelon form. Once we're in row echelon form, we start from the bottom of our matrix and we work our way up until we find the first non-zero row, which is this row. We find the leading entry and we use it to clear the column. I'm going to take row 2 and subtract it from row 1. Now we're in reduced row echelon form. Clearing this 1 from the second column was all we needed. And again, we can translate this into a set of solutions. Our parametric equations are x equals 3 minus 2z, y is equal to negative 2 plus 3z, which we can also translate into the set. In our next video, we'll revisit how to read the solutions from our reduced row echelon form in more depth.